When we last left off, we talked about the difference between floating point numbers and integers. And then we did a quick demonstration of floating point math. And the big thing to remember there is that if you do math with two integers, adding, subtracting, multiplying, dividing, or assigning, I guess as the case may be, the result is going to be an integer. Whereas if you do math with a floating point number, or with two floating point numbers, usually doubles, as that's the default in Java, the result is going to be a floating point number, like a double, usually. And so there are a couple of things that are important to know about floating point numbers. One of those things is that some numbers, like 0.1, that's 1/10, are impossible to accurately represent with floating point math. And the reason for that's kind of complicated and has to do with the way that binary works. But it's important to know that that's the case. And with the double type, your error is going to be somewhere on the vicinity of 10 to the negative 15th, which is 0.13 zeros and then a 1. So it's going to take a long time for that error to add up, but it will add up eventually. This is why we don't use floating point numbers for currency or for anything requiring like really, really precise math, just because of the way that it all works. And so instead of using 0.1, we use a decimal approximation, which in this case is 0.10110110110110110 and so on. This is a lot like how we represent the fraction 1/3 as 0.333, even though it's not entirely accurate. It's a lot like that. And so what that means is that if we do something like this, where float c is equal to 0.1 plus 0.2, we sometimes get something like 0.2999999 under certain conditions, or 0.3000001. It's going to be off by a very, very tiny bit. It'll be off, but only by a tiny bit. And I'll show you this in action real fast. Okay, so we're going to use floats, since floats will add up. The errors in floats is going to be 10 to the negative 7th, which adds up a lot faster than does 10 to the negative 15th. So we've got our increment, which is going to be a 1.1, and the reason that we're casting this is because 1.1 by default is actually a double. So we have to cast this, and I'll explain more about what this means in a bit. We have a result. This is going to be a running sum, and then we have a counter. Okay, and so as long as result is less than 100, this is a while loop. As long as result is less than 100, we increment our counter by 1. Then we increase result by increment by 1.1. And then we print out the steps. And the reason we're printing out the steps is that we can see where the error goes. And so what we should get is 1.1, 2.2, 3.3, 4.4, 5.5, 6.6, where the most that we'll ever actually need to worry about is in the 10ths position. What we're actually going to get, though, is something a little bit more strange. And I'll show you that right now. So when we run this, we're going to get a whole wall of text. Then we're going to scroll back up. Okay, so right here, for example, that should probably be a 100.1. This 0.99915 should add up, but also if we're adding on 1.1 every time, we're getting a lot of decimals that maybe we shouldn't be getting. Okay, and so here, and we can trace this through. So we have at first, we have 1.1, 2.2, 3.3, 4.4, 5.5, 6.6, 7.7, 8.8, and then we get this 9.900001. Okay, so we're off by 1, what is that, 10th, 100,000th, 10,000, 100,000th, we're off by a millionth. And then, before too long, we're off by 2 millionths. Now we're off by 3 millionths, by 4 millionths, by a little bit more. And then, okay, now here's the interesting thing. At right here, we see our error goes all the way up to 8, back to 6532, and the reason for that is because 0.5 is this 38.5 is really convenient to represent in binary. And then now the error starts counting down. Like, this is a rounding error. This is Java incorrectly predicting what's supposed to be happening. Like, what we should be getting right here is a 66 and then a 67.1. That's not what we get at all. Instead, what we get is different numbers. This is floating point errors. Now we're going to use, and this is very specifically because we use the floats. If we used a double, it would take a lot longer for this error to propagate in such a way that we actually notice it. And there are a couple of ways that we can work around it. One way is we can just make sure that we do our rounding a lot more judiciously. If we know for a fact that we're adding on 1.1 every time, we can just round to the nearest tenth. As there's no way that you can add, in real math, there's no way that you can add a whole bunch of 1.1s together and get anything out in the hundredths or thousandths or millionths range. That just isn't possible. The other thing that we might do is use a fixed point class like big decimal, and that's well beyond the scope of this course. I just want you to know that this type of error exists, specifically with floats. With doubles, though, it takes a lot longer, a lot longer, in fact, to get to where that error actually matters. On the quiz, you might see a float. We collect a float using the .nextFloat method. If on a quiz, every time you see a float, you change it to a double, I think that is more than fair and more than reasonable. In our course, anytime that we're going to use a floating point number, we're just going to use a double. Okay, so in the real world, rounding errors generally mean that we should avoid using floating point numbers for currency, for scientific constants, or any situation where that rounding error is going to get us in trouble. In this course, it doesn't matter all that much. In the real world, it probably matters a lot. Okay, so when you talk about numeric types, now that you know some of the dangers of using the float and why you should maybe use the double, when we talk about the numeric types, all the number variables are arranged hierarchically. That is to say that they're arranged from smallest capacity to largest capacity, and then from ints to doubles. And so we'll see something like this, where we've got the byte, the very humble byte down at the bottom, that goes from -128 to +127, the short, the int, the long, the float, and the double. Okay? And so this is, so we'll see something like this, which is to say that we're going to, that these are hierarchically organized such that double is sort of at the top looking down, then the float, then the long, then the int, then the short, then the byte. And we're only really going to worry about ints and doubles in this course. There aren't very many situations where you'll have to use a long or a short or a byte. Okay, now since we only have integer arithmetic and floating point arithmetic, which are very different. Integer arithmetic produces integer results, floating point arithmetic produces floating point results. We have to make sure that we're really conscious of which number type we're using. And you have to be even more careful because Java, when doing arithmetic, requires that the numbers involved are of the same type. And this might seem a little bit onerous, but it's not quite as bad as it looks. Anytime we have an arithmetic operation, plus, minus, times, divide, mod, equals, any of those, let's say that we have like an integer plus a double. What Java will do is it'll automatically promote the thing that's lower on the hierarchy, in this case the integer, up to the level of the thing that's higher on that hierarchy. So if we had an integer plus a double, that integer would get moved up to a double. It would be temporarily promoted. Its value, I guess more specifically, would be temporarily promoted to the same level as the thing it's being added to. And so here's an example of that, right? So we have double A is equal to 3 divided by 7.3. So we have an integer divided by a double. So the first thing that's going to happen is we have an integer and a double. Then we have the integer getting promoted to a 3.0. Now if we had a variable there, if instead of a 3.0 that was a variable, we wouldn't be doing anything to the variable itself. We would just be worrying about the value stored in that variable. So we promote the 3 to a 3.0. And then from here, since those are the same, we do our division, and then we get some results. Okay, so this whole process that's called promotion, because we're taking things from lower on the hierarchy to higher on the hierarchy, and it happens automatically and behind the scenes. Anytime that you have a mismatch in type between two different numeric types, anytime that happens, the lower value automatically gets promoted. And for each of the operation anytime you're going through and solving a complex mathematical equation, the Java virtual machine, or sometimes the compiler, first checks to see if promotion needs to happen first. There is a more complicated bit of math. 7.3 plus, in parentheses, 2 times 4 minus 2 divided by 0.5 plus 1. We know from order of operations that 2 times 4 is going to happen first. And since those are both integers, our result is going to be an integer. So now we have 7.3 plus 8 minus 2 divided by 0.5 plus 0.1. Or plus 1, sorry. From here, we know that we've got, we handle our division, since that's the multiplicative operator, we handle that first. So that 2 divided by 0.5, our 2 gets promoted to a 2.0, so now we have 2.0 divided by 0.5, which is going to give us a 4.0. Now we have 7.3 plus 8 minus 4.0 plus 1. We do addition and subtraction from left to right. 7.3 plus 8 means that we have to do 7.3 plus 8.0 minus 4.0 plus 1. That 7.3 plus 8.0 gives us 15.3 minus 4.0. Those are the same type, so we don't worry about them. We just do some subtraction. Now we have an 11.3 plus 1. And then that 1, since we have a floating point number and an integer, 1 gets promoted to a 1.0. And we add all that together and get a 12.3. So that's our result. And the big thing to recognize here is that we don't, like when we're talking about expressions, we don't just go ahead and promote everything right away. We promote it as we get to it. Now let's say that we want to very finely control exactly where and when promotion happens. Let's say that we want that, instead of having it being done automatically. Then we can use a technique called the Unary cast. It's called Unary because it only takes one argument, and then cast because we can think of it as like we're molding it into a different type. And the way this looks, very basically, we have whatever our new type is. That might be an int, a double, a float, something else, and then our original data, whatever that value might be, whatever those variables might be. So here's an example. Okay. So if you go double C is equal to, in parentheses, double, then in more parentheses, 3 divided by 2, then what's going to happen is we're going to handle this Unary cast. What we're going to do is look at the division first, but in order for division to happen, we have to first do this Unary cast. Okay, and so we're going to take whatever is in these parentheses, or whatever is immediately to the right of the Unary cast, promote that to a double. So now we have 3.0 divided by 2. We have to promote the 2, so that way we have two floating point numbers. Right now we have a floating point number and an integer. So we have 3.0 divided by 2.0. And at the end we just have a 1.5. Or a 1.5 followed by a whole bunch of zeros, more specifically. So we do that floating point division and assign the results. And there might be a very tiny rounding error, but probably not. And we can also use, the Unary cast to promote, which is to say to like go from an int to a double, or you can use it to demote, to go from a double to an int. So you might go do something like int a is equal to, in parentheses, int, and then we have pi, 3.141592654. But what we're going to do is turn this into an integer, which means we chop off everything after that decimal point, and then we're left with 3, which isn't quite the same as pi. Okay. And we can also, if we feel so inclined, cast without that second set of parentheses. We just have to be really careful about it. So we can do something like int a is equal to, in parentheses, int, and then 3.141592654. That will still work, but it's a lot easier to read if you make sure that you have those parentheses around it. And when we come back, we'll talk about, I'll show you promotion, demotion, and casting in action. And then I will also show you a couple of errors that you might make while doing the Unary cast. And we'll be back in just a second.